Thanks for joining me again. Today we're going to continue going through some things on the periodic table, specifically talking about periods and groups and looking at different areas of the periodic table by their names and by their characteristics. So not just metals, nonmetals, and metalloids, but specifically certain areas within each. So we're going to be looking at just naming what groups and periods are, and then specifically naming several of the groups in the periodic table and kind of talk about their characteristics. Some of the vocabulary will be what a period is, a group, earth metals, alkali earth metals, halogens, and noble gases. When we look at our periodic table, obviously it's just a big box with a lot of little boxes in it, but there's a couple of words that we can use when we're talking about the periodic table to make sure that we're describing it properly and that we have a common vocabulary with it, and those are the words periods and groups. It's just kind of a fancy way of saying period is a row, and a group is just going to be a column going down. Okay, so you can see there are 7 periods on the periodic table. And if you go through and count up all the groups, there ends up being 18 different columns that we have there. There are some similarities of elements in the same period. There's some similarities of elements in the same group. So within a period, what we see is all the elements have the same number of electron shells. So for example, in the 4th period, everything has 4 shells. If we went through and drew them, they would all have a similarity. If we were doing a Bohr model, if this is our nucleus, that we do have 4 electron shells, and then as we move across the periodic table, basically we're adding electrons either in the 4th shell, or in this case, with the transition metal going back into the 3rd shell, until we get to the very end, when we would then, if we began the 5th period, we would end up having to have another shell there. Okay. So that's our similarity of elements in the same period. Elements in the same group also have similarity as well. They have different numbers of shells because different periods have different numbers of shells. But the way that they're similar is that their outside shell, in this case, like in the first group, they would all have 1 electron in their outside shell. They would differ because period 2 would have 2 shells, period 3 would have 3 shells, period 4 would have 4, and so on. So a lot of times what we see is that elements in the same group, they're really, really a lot alike simply because they have the same valence electron structure. Their outside shells are identical to one another. Okay, so elements in the same period may have some similarities with their neighbor. If you've got a metal over here, it may be kind of similar to a metal next to it. But in general, what we tend to see is that elements share characteristics much more so if they're in the same group. So this group where I'm putting all these X's, even if we didn't know anything about them, because they're in the same group, or another word that's used sometimes as a family, these elements would all tend to behave the same, or they may share a lot of physical characteristics, physical properties, and chemical properties. They wouldn't be identical because structurally they're just not exactly the same, but they would tend to behave and they would tend to react in very similar ways. So that, again, that has to do with their electron structure, and particularly the outside shell, those valence electrons. If we go across the periodic table, there are, I guess, 4 main groups that we can kind of talk about specifically. The first one is group number 1, which is the alkali metals. You see some pictures there on the bottom, lithium, sodium, potassium. And then as you get bigger and bigger and bigger, these are a little bit more rare. In general, smaller elements are more common than larger elements. You can see there's some similarities in the way that they look. Those would be their physical properties. Some of these are really soft. I've actually been able to handle some of these before, and you can literally cut them with a knife, which is weird because we normally don't think about that with a metal. One of the things we do see, again, the reason they're all in the same group is because they all have 1 electron in their outside shell, if we were just talking about like Bohr model orbitals. So we got lithium, sodium, potassium, rubidium, and so forth. So these are our alkali metals. This is group number 1. They're by far the most reactive metals, and the reason why they're very, very reactive is because they only have that 1 electron on its outside shell. That 1 electron apparently doesn't like to stay there very often, and so that electron is easily lost. It's easily pulled off, which is going to cause this to become a charged atom, which would be an ion. And when that occurs, again, these are going to want to bond with something else to become neutral again. And so these are highly, highly reactive. In fact, it's really rare to just find elemental lithium or sodium, which looking like these pictures down here, because regular sodium, regular lithium in particular, you have to even store it in special things like glycerin or some kind of an oil in order to prevent them from reacting just with the water that's in the air. That's how reactive they tend to be. The second group that we've got here is the alkali earth metals. It's a very similar term. The other one just left out the word earth. So this is our second shell, or excuse me, not second shell, the second group that we have here. And you can see if we did the SPDF notation, again, as we go from beryllium down, we go from 2s to 3s to 4s to 5s because that has to do with the period. But you'll see the valence electron stays the same. All of these end in an S2. So kind of like the previous group all had one electron in their outside shell. All of these tend to have 2 electrons in their outside shell. They're also very reactive. They're not quite as reactive as group 1. They lose, that's supposed to say lose those electrons. I should fix that real quick. Although I can't fix it on the screen, I can do that. They lose both of those electrons in order to be able to react. And again, they're rarely found just in an elemental form like this. They're not as reactive as group 1, but they are super reactive. Now, across the middle of the periodic table, not really a group, but it's kind of a big block here. These are what we call our transition metals. These are the ones that have a D suborbital and take up the majority of the periodic table. So they tend to be less reactive, a little bit more stable. They make up the majority of elements. We see a lot of things that you are probably familiar with: gold, silver, copper, iron, titanium, things that have been around in human knowledge for hundreds, if not thousands of years. And this makes up a large portion of the periodic table. Keep going over to the right, and we'll come back to this in just a second. You'll notice we skipped some of these. We're not naming 13, 14, 15, 16. But when we get to 17, we do start naming them again. And these are nonmetals. We're on the other side of the periodic table. These are halogens. And if you go down, you see fluorine, chlorine, bromine, iodine. These are all nonmetals. They tend to be gases and liquids as you get further down the column or the group. They are also very reactive, just like on the other side is group 1 is very reactive. The reason why is kind of like group 1 only has 1 electron. Group 17 is missing 1 electron, basically to be full. So it's extremely reactive. They like to kind of pull that electron in and react with something. At the very end, though, this is our noble gases. The noble gases are group 18. They are effectively non-reactive. The reason they don't react is their electron shells are completely full. Helium has its 2 electrons, so its shell is full. Everything else has its 8 electrons in its outside shell. So they're full, they don't react. And these were really recent discoveries simply because scientists didn't really know how to find them, because the lack of reactions, they just kind of went unnoticed up until the late 1800s, the early 1900s. Because of their ability to not react, they're used in a lot of industrial processes because they, again, don't start fires and they just don't really do anything. So sometimes when you need a gas that's not going to react, this is a good one to use. Finally, there's a big hunk of the periodic table that you may see down here at the bottom. And these are what we call synthetic, which means man-made or human-made. These are not natural. So a lot of our periodic table, these are things that were made in a laboratory. They're going to be made in a laboratory pretty much by taking large elements and then kind of banging them together so that they stick. And in a lot of cases, these are not very stable. They tend to be radioactive. There's also one, number 43 here, that's kind of in the middle, but it doesn't really exist either because its natural state is also radioactive, and there's not really any of it left around on Earth. So most of these are extremely radioactive. They don't occur in nature. They're only made in laboratories. A lot of them are named after scientists like Einstein and Fermi, or they were named after science laboratories in California or Berkeley or in America. So some of them have some interesting names to them, but these are not things that you end up digging out of the dirt, right? In summary, periodic table has 18 columns. We call those our groups. These are going to be elements in the same groups, usually very similar in their properties. So if we know where, for example, lithium is, we should be able to predict that other things in the same group are going to be very similar. We've got 7 rows, which we call periods. And despite the 118 little boxes on the periodic table, hydrogen and helium actually make up 98% of the universe, and are going to be the 2 most common things that we come across.